In December of 2024, Google published a blog post announcing its newest quantum processor, a chip called Willow, and buried inside that otherwise fairly technical announcement was a single paragraph that would go on to spark one of the strangest, most genuinely contested debates in modern physics. Hartmut Neven, the founder of Google Quantum AI, wrote that Willow had completed a specific computation in under 5 minutes, a calculation that would take one of the world's fastest classical supercomputers an estimated 10 septillion years to complete, a number so large it exceeds every known timescale in physics and dwarfs the age of the universe many times over. And then came the sentence that made headlines everywhere, from mainstream science outlets to conspiracy forums. Neven wrote that this result lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, crediting the idea to physicist David Deutsch. This is the real story behind the headline you clicked on, and I want to walk you through it carefully, because unlike some of the more fabricated viral claims floating around about quantum computers, this one is genuinely real, genuinely controversial, and genuinely worth understanding on its own terms. Now let's start with the actual experiment itself, because the headline number is real, and it's worth sitting with before we get into the far stranger interpretive debate surrounding it. Willow is a superconducting quantum processor built from just over 100 qubits, cooled to a temperature colder than deep space inside a specialized refrigerator, following the same basic hardware approach Google has used for its previous generations of quantum chips. The specific benchmark Neven was referencing is called random circuit sampling, a task deliberately designed to be almost impossibly hard for a classical computer while remaining natural for a quantum one. It works by running an enormously complex, carefully structured sequence of quantum operations across the chip's qubits, and then measuring the resulting probability distribution of outcomes, a calculation that, because of how quantum superposition and entanglement work, requires tracking an astronomically large number of possible quantum states simultaneously, a number that grows exponentially with each additional qubit you add to the system. For a system with just over 100 entangled qubits, that space of possible states becomes so large that no classical computer, however powerful, can feasibly simulate it by brute force by keeping track of every possibility directly, which is exactly why Google's claimed 10 septillion year classical runtime, however staggering it sounds, isn't simply an exaggeration, it's a genuine reflection of how explosively the computational difficulty of this particular task scales as you add qubits. Now here's where things get genuinely strange, and where Neven's comment about parallel universes actually comes from, rather than being an invented flourish added by some later clickbait video. To understand it, you need to understand a real, serious, and long-running debate inside physics about what quantum mechanics is actually describing when it talks about particles existing in superposition, a blend of multiple possible states at once until measured. The dominant, most widely taught interpretation of quantum mechanics is called the Copenhagen interpretation, which treats a particle's superposition as a description of probability, essentially saying the particle doesn't have a definite state until it's measured, at which point the wave function collapses into one specific, definite outcome. Under this view, there's no need to imagine other universes at all. The mathematics is simply describing our uncertainty, or perhaps a genuine physical indeterminacy about a single, definite reality. But there's a second, considerably stranger, and still genuinely respected interpretation called the many worlds interpretation, developed originally by physicist Hugh Everett in the 1950s, and subsequently championed, refined, and popularized by Oxford physicist David Deutsch, a legitimately important figure in the actual history of quantum computing, not a fringe outsider. Under this interpretation, the wave function never actually collapses at all. Instead, every possible outcome of a quantum measurement genuinely happens, but each different outcome plays out in its own separate, branching universe, meaning that every time a quantum event occurs, the universe effectively splits into multiple parallel versions, one for each possible outcome, with each version continuing onward as its own complete, independently evolving reality. Deutsch, in his 1997 book, The Fabric of Reality, made a specific and genuinely influential argument connecting this interpretation directly to quantum computing. He proposed that a quantum computer's extraordinary computational power comes precisely from performing calculations across many of these parallel universes, simultaneously, essentially recruiting the computational resources of countless branching realities to explore an enormous number of possible solutions all at once, before those parallel branches interfere with each other in a way that amplifies correct answers and cancels out incorrect ones, producing the single result we ultimately observe when we measure the final outcome. This is exactly the argument Hartmut Neven was invoking when he wrote that Willow's staggering performance lends credence to the multiverse interpretation. His reasoning, echoing Deutsch's decades-old argument, runs something like this. If Willow really did complete a calculation that would take a classical computer 10 septillion years, a number that vastly exceeds not just human history, but the entire age of the observable universe, then where did all that computational work actually happen? A classical computer, tracking one possibility at a time, clearly couldn't do it within any reasonable time frame. But if you accept Deutsch's many worlds argument, the answer becomes considerably less mysterious. The calculation didn't happen in a single universe at all. It happened distributed across an enormous number of parallel branching universes simultaneously, each one exploring a different piece of the vast computational space, with the final measured result representing the product of interference between all of those parallel computations, exactly the way Deutsch originally proposed quantum computers should work, if his interpretation of quantum mechanics is correct. It's crucial, at this point, to be honest and precise about exactly what kind of claim this is, because this is exactly where the more sensationalized coverage of this story tends to run off the rails. And it's worth being careful here, rather than just repeating the most dramatic possible framing. Nevin's statement and Deutsch's underlying theory is an interpretation of quantum mechanics, not a new, independently verified physical discovery. This distinction matters enormously in physics. The actual mathematics of quantum mechanics, the equations that predict how qubits behave, how they interfere with each other, and what results you'll measure at the end of a calculation, are extremely well established, thoroughly tested, and not remotely in dispute among physicists, regardless of which interpretation you personally favor. What remains genuinely unresolved and actively debated is the deeper philosophical and physical question of what that mathematics actually means about the underlying nature of reality, whether it implies a single universe with genuine quantum randomness and wave function collapse, as the Copenhagen interpretation holds, or countless branching parallel universes that we can never directly observe or communicate with, as the many worlds interpretation holds, or one of several other serious competing interpretations that physicists have proposed over the decades, including pilot wave theories and various objective collapse models. Willow's impressive computational performance doesn't resolve that debate, and it can't, because all of these competing interpretations make the exact same testable, verifiable predictions about what a quantum computer's measurement outcomes will be. Willow performing an extraordinary calculation is fully consistent with the Copenhagen interpretation, just as much as it's consistent with many worlds, which is exactly why so many physicists pushed back hard on Nevin's framing once his blog post started circulating widely. And push back they did, immediately and publicly, which is itself an important and often overlooked part of this story. Physicists writing in response to Nevin's comment pointed out that invoking parallel universes simply isn't necessary to explain how Willow works at all. Most working physicists continue to operate comfortably within the more conservative Copenhagen framework, treating quantum states as probabilistic mathematical descriptions rather than claims about physically real, branching parallel realities. And from that more mainstream perspective, quantum computers gain their power not by somehow outsourcing computational work to other universes, but through the careful, well-understood manipulation of quantum probability, amplitudes, and interference effects, all occurring within our own single universe. No multiverse required to make the math work at all. Critics also raised a more practical, historically grounded concern, claims of quantum supremacy, meaning a demonstration that a quantum computer has decisively outperformed the best possible classical computer at some specific task, have a track record of not aging particularly well. Google's own earlier 2019 supremacy claim, made with its previous generation Sycamore processor, was later challenged when researchers, including a team at IBM, developed improved classical algorithms and showed that a sufficiently optimized classical supercomputer could actually complete the same benchmark task in a matter of days, dramatically undercutting Google's original estimate of how long a classical machine would need. That history matters here because it means healthy skepticism about the precise scale of any single quantum advantage claim, Willow's included, is a reasonable, evidence-based scientific instinct, not simply reflexive contrarianism, and several physicists explicitly invoked that history when responding to the multiverse framing specifically. There's also a subtler, more technical critique worth understanding, one that gets at exactly why so many physicists found Nevin's specific wording lends credence, somewhat overstated even on its own interpretive terms. Quantum interference, the phenomenon where different possible computational paths combine to amplify correct answers and cancel out incorrect ones, a real, well-established, and thoroughly tested feature of quantum mechanics, doesn't actually require you to believe those different paths are happening in separate, physically real parallel universes at all. Under the Copenhagen interpretation, you could describe exactly the same interference mathematics as different possible histories or amplitudes within a single quantum system, without needing to claim that each of those possibilities corresponds to a fully separate, independently existing branch of reality. In other words, the interference effects that make quantum computers powerful are genuinely real and uncontested, but treating them as direct evidence that literal parallel universes exist, rather than simply a mathematical description of probability amplitudes within one universe, is a specific interpretive choice, one that Deutsch and his supporters find compelling and well-motivated, and one that plenty of equally serious, equally credentialed physicists don't find necessary or persuasive at all. It's worth pausing to give Deutsch's side of this argument a fair, honest hearing too, though, because dismissing the many worlds interpretation as fringe or unserious would be its own kind of inaccuracy. Deutsch is not some outsider crank. He's a genuinely influential figure in the actual history of quantum computing, credited with formulating some of the earliest theoretical descriptions of what a universal quantum computer could do, work that helped lay real groundwork for the field decades before companies like Google or IBM built any physical quantum hardware at all. And the many worlds interpretation itself, whatever you make of its stranger implications, is taken seriously by a meaningful portion of the physics community, appearing regularly in serious academic surveys of physicists' interpretive preferences, generally running somewhere in the range of 15 to 20% support among researchers surveyed. A real minority position, not a majority one, but a genuinely serious and actively defended one within mainstream academic physics. Not a fringe conspiracy theory circulating only on the internet. Deutsch's specific argument that quantum computers derive their power from what he calls quantum parallelism, performing calculations across parallel branches that later interfere with each other, is a real, published, peer-reviewed theoretical position that he has defended and refined across decades of serious academic work. And it genuinely does offer one internally coherent way of explaining why a system like Willow can outperform classical computers so dramatically on certain carefully chosen tasks. So where does that leave the actual honest answer to the question buried inside this headline, whether Google's Willow chip really did detect interference from a parallel universe? The honest answer requires separating two things that a viral headline tends to smash together into one dramatic claim. First, did Willow detect, measure, and rely on quantum interference to produce its result? Yes, unambiguously, and this is not remotely controversial among physicists. Quantum interference between different computational paths is a real, essential, well-understood part of how every quantum algorithm, including the one Willow ran, actually works, regardless of which interpretation of quantum mechanics you personally favor. Second, does that interference constitute direct evidence that literal, physically real parallel universes exist, in the way Deutsch's many worlds interpretation proposes? That's a genuinely open, actively contested philosophical and physical question, one that Willow's impressive performance doesn't settle, because every leading interpretation of quantum mechanics, Copenhagen included, predicts the exact same observable result from this exact same experiment. Nevin's blog post conflated these two things somewhat, presenting a specific minority interpretive stance as though the experimental result itself provided fresh evidential support for it. A framing that, however exciting it made for a viral headline, drew immediate and largely warranted pushback from physicists, working across a range of different interpretive camps. It's worth adding one more layer of nuance here because it explains something important about why a company like Google, whose actual technical achievements are genuinely impressive on their own merits, without needing any multiverse framing at all, would choose to include a comment like this in an official announcement in the first place. Nevin's broader body of public writing suggests he holds a genuine, long-standing personal interest in the many worlds interpretation as a serious physical hypothesis, not merely as marketing flourish, and it's entirely possible, even likely, that his comment reflected a sincerely held scientific opinion rather than a calculated hype tactic. That doesn't mean his framing was correct, or that it represented some kind of new evidence beyond what Deutsch had already proposed decades earlier, but it does mean this wasn't some cynical publicity stunt engineered purely to generate viral headlines, even though it very much did end up doing exactly that. Genuinely brilliant physicists and engineers are entirely capable of holding sincere, well-reasoned minority scientific opinions and expressing those opinions publicly, especially when their own extraordinary experimental results feel to them personally like they resonate meaningfully with a theoretical framework they already find compelling. There's a broader, genuinely useful lesson buried in all of this, one that applies well beyond just this single quantum computing headline. Quantum mechanics is, without exaggeration, one of the strangest, most successfully predictive theories in the entire history of science, capable of predicting experimental outcomes with staggering, repeatedly verified precision, while simultaneously leaving deep, unresolved questions about what its own mathematics actually implies about the fundamental nature of reality completely open. That combination, extraordinary predictive success paired with genuine interpretive mystery, is not a weakness of quantum mechanics. It's one of its most fascinating and honestly kind of wonderful features. And it means that legitimate, serious scientists can look at the exact same experimental result, Willow's genuinely remarkable computational performance, and walk away with completely different, equally well-reasoned conclusions about what that result actually tells us about the deep structure of the universe. That's not a sign that something is broken or dishonest about the science. It's a sign that we've built machines capable of probing questions so fundamental, so deep, that our best current theories genuinely don't agree on how to fully interpret what they're showing us, and that honestly might be the single most exciting part of this entire story. So the next time you see a headline claiming Google's quantum chip detected interference from a parallel universe, you now have the full, honest picture behind it. It's not a fabricated event, the way some of the more invented viral AI stories floating around the internet turn out to be. Hartmut Neven really did write those words in an official Google blog post about a real, genuinely impressive quantum computing result. But detected interference from a parallel universe is doing an enormous amount of interpretive heavy lifting in that sentence, quietly smuggling in one specific minority philosophical position about what quantum mechanics fundamentally means, dressed up as though it were a straightforward experimental finding, rather than a decades-old, still genuinely unresolved theoretical debate. The interference Willow relied on to produce its remarkable result is completely real, completely uncontested, and completely essential to how quantum computers work. Whether that interference is best understood as evidence of literal, physically real parallel universes, or simply as elegant probability mathematics unfolding within our own single universe, remains exactly what it was before Willow ever ran a single calculation. One of the deepest, most genuinely unresolved open questions in all of physics, and one that a single impressive quantum chip, however extraordinary its performance, was never actually going to be the thing that finally settles. Let's spend a little more time with the specific mechanics of quantum interference itself, because understanding it properly is really the key to seeing through the more sensationalized framing of this entire story, without dismissing the genuinely fascinating physics underneath it. In a quantum computer, each qubit doesn't just sit in a simple fixed state of 0 or 1. It exists in a superposition, a mathematical combination of both possibilities simultaneously, described by something called a probability amplitude, a value that can be positive, negative, or even involve what mathematicians call imaginary numbers. When you link many qubits together and run a carefully designed sequence of quantum operations, these probability amplitudes combine and interact with each other in ways directly analogous to how ripples on a pond can combine, sometimes reinforcing each other into a bigger wave, constructive interference, and sometimes canceling each other out entirely, destructive interference. A well-designed quantum algorithm is essentially an elaborate, carefully engineered choreography of these amplitudes, structured so that the paths leading to the correct answer reinforce each other constructively, growing stronger, while the vastly more numerous paths leading to incorrect answers interfere destructively, canceling each other out to nearly nothing. When you finally measure the system, you're overwhelmingly likely to observe the correct, amplified answer, precisely because of this careful interference engineering, not because the computer literally checked every possibility one at a time and picked the right one through brute force. This is where the two interpretations genuinely diverge, and it's worth walking through both descriptions of the exact same mathematics side by side, because seeing them next to each other makes the interpretive gap much clearer. Under the Copenhagen interpretation, you describe this process as a single system exists in a superposition of many possible computational paths, described by a single unified mathematical wave function. And interference occurs between these different possible paths within that one wave function, all happening within our one universe, with no need to imagine any of those paths as separately physically real. Under the many worlds interpretation, you describe the exact same mathematics as the universe genuinely splits into many separate physically real branches, one for each possible computational path. And interference occurs because these separate branches actually interact with each other, before ultimately merging back together, or effectively canceling each other out at the moment of measurement. Both descriptions predict exactly the same final measurement outcome, which is precisely why physicists say these interpretations are empirically indistinguishable using current experimental methods. No test performed so far, including everything Willow did, can actually tell you which description is the real one, because both descriptions were specifically constructed to reproduce the identical observable mathematics. This empirical indistinguishability is actually the single most important and most consistently misunderstood fact in this entire story. And it's worth stating plainly one more time because so much of the viral coverage skips right past it. If two competing scientific theories make exactly the same testable predictions about every possible experiment you could currently perform, no single experimental result, however impressive, can serve as evidence favoring one theory over the other. This isn't a limitation specific to quantum computing or to Willow. It's a basic foundational principle of how scientific evidence works. Willow's staggering computational speed is genuinely remarkable evidence that quantum interference and entanglement can be harnessed to solve certain narrow classes of problems dramatically faster than classical computers can. A real, hard-won, and impressively verified engineering and scientific achievement. It is not, and by the very structure of the competing interpretations, cannot be, evidence that specifically favors the many worlds interpretation over the Copenhagen interpretation, or over several other serious competing interpretations, because every one of them predicts Willow should behave exactly the way it did. So why, given all of this, do serious physicists like Deutsch keep gravitating toward the many worlds interpretation specifically, rather than treating the whole interpretive question as a philosophical dead end not worth debating at all? The honest answer involves a real, ongoing, legitimate scientific and philosophical argument about which interpretation is more elegant, more internally consistent, and requires fewer additional assumptions bolted onto the basic mathematics of quantum theory, a genuinely important consideration in physics, where theories that require fewer arbitrary extra assumptions are generally preferred, all else being equal. Proponents of many worlds argue that their interpretation is actually the more economical one, in a specific technical sense, because it doesn't require adding an extra seemingly ad hoc rule to the theory, the mysterious wave function collapse that the Copenhagen interpretation requires, but that never gets fully explained by the underlying mathematics itself, describing instead exactly what the equations already say happens. Every possible outcome occurring without needing to bolt on any additional collapse mechanism at all. Critics of many worlds respond that positing an unobservable, unlimited, and constantly proliferating number of entire parallel universes is itself a far larger, far stranger metaphysical assumption than simply accepting that measurement causes a definite, singular outcome, even if the exact mechanism behind that collapse remains genuinely mysterious and not yet fully explained. Both sides of this argument have real intellectual substance behind them, and reasonable, well-informed physicists genuinely disagree, which is exactly why this interpretive debate has persisted, essentially unresolved, for nearly 70 years since Hugh Everett first proposed it back in 1957. There's also a practical, forward-looking dimension to this story worth including, because it helps explain why this debate isn't likely to be settled anytime soon, regardless of how much more powerful quantum computers eventually become. Some physicists have proposed genuinely creative, if still largely theoretical, experiments that might, in principle, someday distinguish between these competing interpretations under sufficiently extreme and currently unachievable conditions, involving isolating extraordinarily large quantum systems from environmental interference for extraordinarily long periods of time, conditions so demanding that no laboratory on Earth currently comes remotely close to achieving them. Until, and unless, such an experiment becomes genuinely feasible, the interpretive question is likely to remain exactly where it's been for decades, a matter of theoretical elegance, philosophical preference, and ongoing academic argument, rather than something any single quantum computing demonstration, however impressive its raw performance numbers, can settle on its own, regardless of how dramatically a company chooses to frame its own announcement. It's worth closing with a note about why this particular controversy, more than most quantum computing stories, ended up generating such intense and sustained public fascination, because I think it reveals something genuinely interesting about how people relate to strange scientific ideas more broadly. The notion of parallel universes has for decades occupied a strange cultural position, familiar to almost everyone through science fiction, video games, and popular entertainment, yet almost never encountered as a subject of genuinely serious scientific argument in most people's everyday lives. When a company as recognizable and as technically credible as Google put out an official statement that seemed to connect its real, verified hardware achievement directly to that familiar science fiction concept, it created an almost irresistible hook, a moment where a wildly speculative, culturally familiar idea appeared to brush up against hard, verifiable, real-world engineering. Even though, as we've now walked through carefully, the actual scientific relationship between the two is considerably more tentative, more interpretive, and more genuinely contested than the most exciting version of the headline implies. That tension between an extraordinary real technical achievement and a genuinely unresolved philosophical question about what that achievement ultimately means is exactly what makes this story worth telling honestly, rather than either dismissing it entirely as hype or accepting the most dramatic version of it uncritically. Willow is real. Its performance is real. Quantum interference is real. Whether that interference is happening across countless branching parallel universes or entirely within the quiet, singular mathematics of our own one universe remains a question physics has been sitting with for nearly 70 years, and one that, for now, honestly, remains yours to wonder about too. And maybe that's the most honest place to leave this story. Not with a verdict, because physics itself hasn't reached one, but with a clearer sense of exactly what's settled and what isn't. What's settled? 100+ qubit chip, cooled colder than space, ran a benchmark calculation no classical supercomputer could realistically match, using real, well-understood quantum interference to get there. What isn't settled, and may never be, at least not with today's tools, whether that interference is the universe quietly doing arithmetic with itself, or countless versions of the universe doing it together. Google didn't prove the multiverse exists. It built a genuinely remarkable machine and then handed physicists a fresh, real example to argue about, using an argument that's older than the chip itself and will likely outlast it too.